Hi, everyone. This is the start to our week 3 videos, and this week we're talking about the normal distribution. So first, we're going to start with a really quick video about the properties of this distribution. Um, this distribution is one of many possible continuous probability distributions. And a reminder that continuous data is typically data that's measured. It's data that can take on fractions or decimals, like 57.5 inches tall or 2.3 minutes waiting in line at the grocery store. The most common continuous probability distribution we're going to see is the normal distribution. Almost everything we're going to do from this week onward is based on the normal distribution. And it has 7 defining properties. Let's take a look at the picture first. I'm sure we all recognize it. This is the picture from your textbook. And these 7 properties describe that very specific shape. First, it's continuous. We only get normal distributions like this from a continuous random variable. It is specifically bell-shaped, though it is important to note that bell-shaped by itself doesn't make it normal. There are other bell-shaped curves that are not normal, and we're going to see one in about a week or two. It is symmetric about the mean. We can see in the picture, the mean here is in the middle, and that cuts that bell shape right in half. Also important that the mean, median, and mode are all located in the same place. This peak indicates where most of the values are. That's our mode. And because it is symmetric, the median and the mean should sit in the same place. Another interesting fact, and this is true for all probability distributions, is that the area under this curve represents probability. So if I'm interested in the probability that a randomly selected value is somewhere in this range, I just have to figure out the area under that section of the curve. And we're going to learn how to do that in a later video this week. The total area under this curve, since it represents probability, is 1 or 100%, because this curve should represent all possible data points. And the last is that the x-axis forms an asymptote. And what that means is that these tails keep going off the graph forever and ever and ever and ever right off the screen. And the graph gets closer to the x-axis, but it never quite touches. It goes to infinity in both directions. That should make us a little uncomfortable because we just said that the area under that curve is finite. It's fixed at 100%, but the graph keeps going forever. And that's where some hand-wavy calculus comes in. There is a branch of mathematics called calculus that would let us show that even though the graph goes forever, the area under it is fixed at 100%. But because calculus isn't a prereq, we're not going to do that here. I am going to show you the formula that you would use if you wanted to do some calculus, the equation that graphs this curve. You don't ever need to use it for anything. And I know when a lot of students see this equation and they're not like mathematicians, they kind of freak out. I promise you'll never have to use it. I'm not going to ask you about it on the test, but there are 2 important things in it that tell us something important about the graph. So deep breath. This is the equation for that bell-shaped normal curve. And it looks really scary. There's this fraction out in front, which is just a bunch of numbers, and then an exponential base e with my variable x in the exponent. The only 2 pieces of information we need as a statistician is that this function depends on the standard deviation sigma, and it depends on the mean. So there are two numbers that are determining the shape of this normal curve, the mean and the standard deviation. The mean tells me where the center of that curve sits on the number line. So if the mean is bigger, the whole bell shape is going to shift that way. If the mean is smaller, the whole bell shape is going to shift that way. The standard deviation determines how wide or narrow that curve is. It squishes it in if the standard deviation is small, so all that data is packed really tightly about the mean, and it spreads it out and makes it low and flat if the standard deviation is big, because that means the data is spread out far from the mean. And you can see I've included two examples here. Both of them have a mean of 0. We can see they're centered about the y-axis. You'll notice the one that has a standard deviation of 1 is tall and it's narrow. It approaches that x-axis right about 3, a little past 3 on either side. Whereas a graph with the same mean but a standard deviation of 4 is much lower, down at 0.1 as opposed to a peak at 0.4. And it starts flattening out past 8. So it's much lower and it's much wider. Still a bell shape, still normal, but skinny or wide, left or right has to do with mean or standard deviation. That's it for this first video. If you have any questions, feel free to email me or drop by office hours. Otherwise, I will see you in the next video.